Hey everyone. So today we're going to hop back into solving some trig equations for our warm-up, and then also learning about some new, what we're going to call identities. And we already know a few of them, but we're just going to extend that to a new principle and get into a pretty tricky concept, which is called verifying trig identities. So we're going to take a look at that. To start us off today, there is a warm-up, which ideally you can kind of start work on your own, and then I'm going to show you the answers here. So, here's our warm-up. Again, take that break to see if you can't attempt these on your own, but just to go over them real quick. This is a culmination of stuff that we were looking at before break. So I've shown some of these steps here, but I know it was kind of tricky before break. Some people were or weren't able to kind of get through all this, so it might be worth rewatching some of those videos if you need to. Otherwise, taking a look here, you might be able to derive some of that information as well. So there is some factoring that's required on the bottom two. One is going to be a quadratic factoring. The one on the right, factoring out the greatest common factor. And then up top, there's a lot of using the unit circle in order to either undo basically that cosine of x equals root 2 over 2, or there's the other one in which we need to evaluate the tangent of pi over 4. And in both of those cases, you have the unit circle to go off, so it all also should have been stuff from before break. But again, I know we need to work on it, so yeah, hopefully it wasn't too tricky. But even if you couldn't do this, you might be able to still get by with today's lesson until you have time to ask me about it. All right? So for today's lesson, there is an attached worksheet on your calendar which you might want to take a look at that talks about, I'll hand it out on probably like a special green sheet of paper or something like that so that you have it. But there's a lot of rules that we can use with these trig functions. So on the left-hand side here, we've probably seen these rules before. We've talked about them in class, and it shouldn't be news to us that basically cosecant is 1 over sine. Tangent and cotangent are kind of cool. Tangent is 1 over cotangent, but you could also consider tangent to be sine over cosine, which is nice. And what we're going to be learning about today, or proving, is these Pythagorean identities that are on the right-hand side. So sine squared theta plus cosine squared theta equals 1. And it's kind of interesting, but once we prove it, it's like, yeah, okay, that makes a lot of sense. That ends up not being too tricky. And we can generate those other identities on the Pythagorean side as well with relative ease. And this gives us more tools that we can use to manipulate expressions involving trig or solve additional equations, and that is going to be something that we're going to prove before the end of the day. All right, so let's hop into proving our Pythagorean identities and see how that's going to look for us. And I did get a little bit of a head start in that I drew kind of a basic unit circle, and we're going to use those to prove the Pythagorean identity. So if I am taking a look at this unit circle, one thing that I can say, or one thing that I know, is this opposite side, right? This is normally x comma y. And this opposite side is also sine. So this is sine of theta is also my y value. And then cosine of theta is my x coordinate here. And I know that my hypotenuse on the unit circle is 1. If I look at this, even without really knowing that angle measure or the y coordinate or the x coordinate, I can still use Pythagorean theorem here to relate these, which is why, this identity is called the Pythagorean identity. So this is a right triangle. I know my hypotenuse. While I don't know the exact value of my bases, I do know that it's cosine theta and sine theta basically once I have them. So that allows me to say, well, okay, basically a squared plus b squared equals c squared. And the reason I'm not squaring that is just because 1 squared is 1, so I can just leave it like this. And this is our first Pythagorean identity. And it's important to know that we might see it in this form, but obviously we can manipulate this to a variety of different things. So I should be able to recognize that sine squared theta minus 1 is going to equal negative cosine squared theta, right? I'm just subtracting the 1, subtracting cosine squared theta from both sides. I end up with this. And there are other ways to manipulate it, obviously, too. So cosine squared theta equals 1 minus sine squared theta. Okay, any simple change from this initial one is going to end up giving me 4 or 5 other ones that I need to just at least be mindful of. I can also take this initial expression that we've come up with just using Pythagorean theorem in order to prove some of the other ones that we have here. So if I start with sine squared theta plus cosine squared theta equals 1, and then I say, well, okay, what's going to happen if maybe I take each of these and I divide by cosine squared theta? Oh wait, I already had that squared there. Let me just rewrite this. So I'm taking each term and dividing it by cosine squared theta. And then if I use, on the far left, I have sine squared theta over cosine squared theta, which is actually tangent squared theta, plus cosine squared theta divided by cosine squared theta is 1, equals 1 divided by cosine squared theta. 1 divided by cosine is secant, so this ends up being secant squared theta. And then we've basically arrived at another Pythagorean identity. Again, we can manipulate this however we want in order to get some other identities from this. So tangent squared theta equals secant squared theta minus 1 is going to be 1 if I just subtract 1 from both sides. If I start in that same initial spot here, which is sine squared theta plus cosine squared theta equals 1, and then I divide each by sine squared theta this time, then I can also see, okay, this is going to be 1. Cosine squared theta divided by sine squared theta is actually cotangent squared theta. And then on the right-hand side, 1 divided by sine is cosecant, so this ends up being cosecant squared theta. All right, again, can manipulate these, but these are really kind of the distinct variations, or the the core of what we want, being all these different types that we've kind of come up with, and they are the most kind of unique versions of these. Okay. And these become tools that we use to, like I said, verify some of these identities, which we're about to get into. Before we do, I'm probably going to need to make this into a 2-parter, just because my pencil's dying here. So I'm going to stop this video, and then our next video will be on just identifying or verifying the identities below. All right, see you in a bit.